Welcome to homework.
Okay, we are talking about the catalytic hydrogenation of 1,4-dimethylcyclopentene. This is 1,4-dimethylcyclopentene. And something that's worth pointing out is that there's really two ways of drawing 1,4-dimethylcyclopentene. Consider that this carbon right there is actually stereogenic, right? There is stereochemistry at that carbon, right? Because if we go to the right, we see a carbon. It's like bond to carbon, bond to hydrogen, bond to hydrogen. And we go down here, we see a bond to carbon, carbon, carbon. Whereas if we go to the left, well, we still see carbon, hydrogen, hydrogen. When we go here, we only see carbon, carbon, hydrogen, right? So this bond has higher priority. And in fact, we see that depending on whether or not that methyl is in the front or the back, let's assume it's in the front for now. This would be priority 1, priority 2, priority 3. This, for example, would be S, right? Whereas we could also have sorry, I forgot to put the hydrogen here. Where we could also have R. Okay, this is worth pointing out because this is going to matter. In fact, the better way, perhaps, to even draw these would be as follows. I'm going to draw a wedge to the methyl there, and I'm going to draw a dash to the methyl there. Okay, next, remember that we're talking about catalytic hydrogenation. That means reacting with, say, H2 over a palladium on carbon surface, right? And recall that this actually means something's happening at a surface, right? So one way we often conceptualize this happening is that imagine that we have some surface, and this is palladium on carbon, right? And we're doing it in H2 gas. What actually ends up happening is that we get a bunch of hydrogen sticking to the surface of the palladium. And that what's going to happen is that an alkene comes down here, right? And typically it's going to orient such that its least hindered face is towards the surface, and it's going to grab a hydrogen while it's simultaneously being attacked by a hydrogen. The point being that those hydrogens, let me color these in real quick, will end up on the same face of where the double bond used to be, right? There's something that's going to make that happen, right? Okay. Another thing maybe that would help if I pointed out is that this is, I don't know how to draw this as like a side-on view. Like these p orbitals are going down, up and down, right? So the bond is probably like hydrogen here already coming towards us, and then maybe some carbons in the back, right? Yeah, right. If this is like this, then what we're viewing is actually, from the side on would be like the R groups going straight back and the hydrogens coming straight towards us, and the p orbitals of the double bond going literally straight up and down. And that's what's interacting with the hydrogens on the surface of the palladium. So hopefully that makes some sense, because that's where this question is coming from. What they're saying is that this molecule, in order to get hydrogenated, is going to have to settle onto a surface of palladium on carbon with hydrogen attached to it, right? So consider how these molecules would look if this double bond, if we were looking at them edge on. Maybe I'll do one of them in green to make it more obvious. Okay. So let's consider viewing these molecules edge on. All right, so we're going to have the blue bond, and then I'll draw a little bit of perspective, right? And this one's got that going there, and this one, methyl group coming out towards us. Maybe I'll draw that as a wedge. Me for methyl. Okay, so hopefully you can see what I'm talking about here, but what I'll point out is that if this is a wedge here, that's actually going up, and if it's a dash here, that's actually going down, right? And so when we approach the surface that we need to attach to pick up our hydrogens and get hydrogenated, I'll just be a little more clear here. There's a double bond. Okay, when we approach that surface, in the case where we have the pointing downward thing here, right? This methyl is interfering with the surface here, right? There's repulsion. The surface is repelling the methyl. The methyl's repelling. The methyl is pushing away the surface. The surface is pushing away on the methyl, and this is the unfavorable version, basically, right? So what's going to happen is that basically what you end up with is this version. Is favorable, whereas this version is unfavorable, right? So the version where the hydrogen adds to the opposite side of the methyl is favorable compared to the version where the hydrogen adds to the same side as the methyl. And then we consider that if we draw a dash to hydrogen here and a straight line to methyl there, that's the same as, say, drawing a wedge to a methyl here and not drawing the hydrogen at all. Right. Similarly, if we draw a dash to a hydrogen and nothing to this methyl, that's the same as drawing a wedge to the methyl and nothing to the hydrogen. Right? So basically what this is saying is that we can either end up with cis methyls or we can end up with trans methyls. That's really all there is to it. And the version where we get cis methyls is this version here. These methyls end up cis. Okay, so the cis methyl you end up with 10 times more of than you do the trans methyl. So the major product is simply cis 1,3-dimethylcyclopentane, whereas the minor product is trans 1,3-dimethylpentane.